Well, good evening, everybody. I'm Ralph Weir. I'm the CEO of Cambridge Nanotherm, and thank you ever so much for the opportunity of coming along and talking this evening. Good evening. So, where do we fit in to this whole British manufacturing thing? Well, we build the world's best materials for thermal PCBs, and we do it in Cambridge. Actually, it's a small, dark secret. We don't build them in Cambridge. We build them in Suffolk. But we started the business in Cambridge, so we're going to stick with it. The Japanese know where Cambridge is. It's North London. The other surprise is that these materials are actually very cost-effective, and yet they're built in Britain. So I'll spend a moment or two looking at how that came to be. Here's a factory up in Haverhill. We're a high-tech business, established in 2010, commercializing some technology that had actually been developed in Moscow originally for aerospace and is now being applied in the electronics industry. It's a patented technology for moving heat around, for filtering out energy. So it moves the heat, it keeps the electricity where it is. And you can see the advantage of that in the electronics industry. You can see here on the right, we've got a few people in our fan club, a few people giving us awards. On the left, I'm told the word is recognition. In terms of recognition from UL for the materials and for the factory, and also ISO 9000 for the factory. So you can see we've moved commercializing this material from what was an academic project maybe 10 years ago through to founding the company 4 years ago. UL, ISO 9000, it's a proper product these days. We're starting to get out there. You may have seen some of the noise that we started to make. Shamelessly stolen one of Lee and Steve's images there with the Go Naked program, wrapping through to pictures of the high volume production line that we've now got set up. It's not just us saying that this is good material. You'll see a quote from one of our friends, I saw it coming in, saying that actually this stuff is good. I can show you a few of the people who are playing with it and evaluating it and moving it forward into production. So there's a challenge that we have in our industry. It's something that we need to look at quite hard in terms of education of some of our engineers. This is something I hear all the time, is I want a 2-watt material. And, sorry, what is a 2-watt material? There's a few letters missing there. In the Scottish vein, watt, he'd be Scottish. Kelvin, he'd be Scottish. I don't know where meter came from. French, I suppose. We've got them surrounded, doesn't matter. But that's the thing, is people say 2 watts, that's tradition, that's what we use. And they forget that the semiconductors are changing, they're getting smaller, they might be getting more efficient, but they're getting smaller, that means they're getting hotter, that means the problem is increasing. They're also misunderstanding the problem. If you just say 2 watts, that's good enough, you miss some tricks. And here's a few of the tricks. By using nanotherm technology, the UK lighthouses have managed to give themselves a 2.5 times increase in light from the same LED lamps. It's the same semiconductors, same drivers, same everything, 2.5 times increase in light, and a 16 times increase in expected lifetime. You can imagine that's a great combination for a lighthouse. People curing inks on digital printers, double the throughput. Now these printers are not cheap, and yet you can double the throughput on many of these printers just by increasing the UV light output. And that's all about getting more heat out of the UV LEDs. How about this one? Consumer light bulbs. Imagine you could half the cost of consumer light bulbs. Well, that's exactly what one of our customers is doing. Thermoelectric generators. It's looking at heat in a slightly different way. It's not, I've got some electronics which are getting hot, can you get rid of the heat? It's, I've got something which is hot, I'm trying to generate electricity from it. Can I get more power out of it? And of course the answer is yes. If you can flow the heat through more efficiently, you can do exactly that. So what we're doing here is using high technology to get more out of less. And that's going to be absolutely critical to keeping jobs in Europe, keeping us at the forefront, keeping us cost effective. Talk a little bit about how it actually works. And if you've looked at thermal management, I'm sorry, that graph is probably not very clear, but if you've looked at thermal management and the effect of various materials, what you find is that the better something conducts heat, the better it conducts electricity. It's a bit of a pain. This is why a lot of people have aluminium pots, because the heat goes through quickly. A lot of people prefer stainless steel pots because the heat goes through slower, which gives you a nice gentle simmering or something. But that's the nature of the game, and you can draw a straight line and you find that even rubber is pretty much on that line. What made me giggle was wet wood and damp wood are in different places on the same line. They are very much on this linear relationship. There are a few materials which stand out, and there's an example, alumina. Sits there, it conducts heat better than some metals, it conducts electricity at about the same level as rubber. It's basically an insulator. So what we do is we combine a very thin layer of alumina onto a piece of aluminium. Now, if you can read that graph, you're probably going, aha, you've only run the graph out to lead, and we all know aluminium is a much better conductor of heat than lead. So what we've taken is one of the most conductive metals in aluminium, heat-conducting metals, and we've wrapped it up in a very thin layer of alumina, which is a very, very heat-conducting ceramic. So you've now got an insulated piece of aluminium. Massively more effective than the traditional options. There's where it sits. So now, there's aluminium. Where we had lead is now down here, and you can see the compound conductivity is sitting at about 115 watts per meter Kelvin for this particular material. That's our baseline material. We've got better things than that. But that's the baseline, 115 watts per meter Kelvin. Another quote from that kind of man. So, again, the awards, the recognition, what we're looking at here is something which is a very clever electrochemical process. We're treating large sheets of aluminium through a large process, which is largely automated. Take the metal sheets, drop them into the machine, come back 10 minutes later, and there's a pile of plates processed with the ceramic on. What that means, if you compare with the competing solutions, I'm sorry that hasn't come out particularly well, but you might be familiar with the resin-based metal PCBs. In a resin-based metal PCB, you start with a sheet of aluminium or copper, you put a resin on top, you might load the resin with something that helps it conduct heat better, perhaps a finely ground ceramic, which is expensive, perhaps even crushed diamonds, which is hideously expensive, and then you put a sheet of copper on top of that. And that's great. That's where the industry's been for 10 or 20 years. Performance has been getting better. It's kind of hit a bottleneck at around the 3 watts per meter Kelvin mark, 3 to 4. It's just one of those things that the more fillers you put into resin, the thicker you have to make the resin, and you're on to diminishing returns. You end up with a thicker layer which might conduct better, but because it's thicker, you're conducting further, and you're not actually moving forwards. In contrast, here's what we have. So we have the same layer of copper mounted on the same layer of aluminium, but in between we now have a very, very thin layer of ceramic. This line here, I'm sorry, this is quite poor, this drawing on the display, but this line here, that's the point that in this material, our Nanotherm LC, that's the point that we're transferring out the dielectric into the metal. You can see over here, from there to there is the dielectric. So at the point we're putting the heat into the aluminium, our competitors are only a third of their way through the dielectric. So you can imagine the effect that has on performance. That's the kind of effect. This is where we claim the dielectric sits, at about 7 watts for the dielectric itself. 115 is a composite number, and there's some of our competitors. Those are basically spot pricing of what we're seeing out in the industry for these various materials. You can see that up the way is bad, up the way is cost, over to the right is goodness, it's performance. So really where you want to be is low down, over to the right. There are materials out there that we can't today compete with in price. Remember, they've been building production lines for 20 years on that process. We're building we've just completed our first fully automatic line. So we've got a long way to go down the cost curve, and yet we're already trashing materials that only have half our performance. What that means, taking an example from the high brightness LED market, You can see this is an LED downlighter driven at different power levels. Now, if you imagine those power levels are pretty much directly related to the brightness of the lamp. If you said that we could cope with about a 20-degree temperature rise, you can see that with Nanotherm, we can drive it to 1.5 amps. With brand 2 and brand 3, you're down at 1 amp. So you're only at, or the Nanotherm is 50% brighter. With brand 4, you're down at 700 milliamps. So Nanotherm is actually delivering twice the brightness as that other premium grade metal PCB. It's probably cheaper than that other metal PCB as well. Why does all that matter? Look at this. This is a breakdown of LED build costs. Now, I'm using the LEDs as an example, but this is applicable to many industries. Anything that's using semiconductors, if you can manage the temperatures, you can generally drive the semiconductors harder. So there's a breakdown of the costs of an LED downlighter, and you can see that something like 45% of the cost is the LED, 11% is the cost of the lens that goes with the LED. So 56% is directly attributable to the cost of your LEDs. Every LED needs a lens. And the amount that goes on the PCB is about 5%. So imagine you doubled the amount that you spent on the PCB. If that would just half the amount that you're spending on the LEDs, you've got a huge benefit. And I've just shown you something that says you're not going to spend double, you're going to be spending less. So there's the interesting sums. What our customers are doing, as we started off with the lighthouse guys, or the UV printing guys, twice the light out, or as we're talking about the commercial consumer grade light bulbs, you get half the price. Very, very attractive. Oh, of course, if you're using copper boards, we don't see the same performance benefit using this material against copper. It's still fractionally better, but it's only a few percent better than a copper board, but it's about half the weight, quarter the weight. It's a much more cost-effective material than the copper material. So this is something that's very, very interesting no matter where you sit in the industry. What we're doing with it, the first product, the one I was talking about a moment ago, we're putting into the metal PCB market. Very clear, competing against materials from people like Bergquist, Ventec, Laird, very, very capable, very competent companies, but going out there with something which has got significantly higher performance and a fundamentally lower cost base. The second area is going out against aluminium nitride ceramics. And this, for the PCB industry, may be something a little new in that traditionally processing ceramics is extremely difficult. It involves a whole new set of etch chemistry that is fairly unpleasant. And yet we're saying here is essentially a metal PCB technology that takes you into that world. And that's a significant opportunity for PCB vendors, is to go after the aluminium nitride market. You'll see a different set of names there as the companies we're up against. People like Rogers, Murata, Kyocera, Tongsing, a lot of Asian companies in there. And that market, a lot of it is to do with semiconductor packaging. So it's perhaps not so much of a European market, perhaps driven out of very, very high volumes out in Asia. This next slide perhaps labours the point a little bit. There we are, there's a metal PCB, that's where we sit. The second market is then within the substrate of the LED package itself, which is a very similar market to the IGBT market. There's another thing that we're starting to work in. This is working very much with mobile phone companies, where they have very high density circuit boards within the phone, which have to cope. Although we think of phones as being relatively low power, they have to cope with the applications processor. And the applications processor packs everything into such a tiny area. It's a real hotspot. The thermal density around that is nasty. And yet you've got something which you can't have a fan in a mobile phone, you can't get the heat out. So how do you do it? In some cases you also have to cope with the board being flexible. How about you put a very thin layer of this aluminium in? It's an insulated layer, it's a heat spreader, it can go into a thermal board, a flexible thermal board. So, a final example. I mentioned the thermoelectric generators. This is a market that people are out there just now talking about this as being a real market in terms of where it sits against something like LED. LED is certainly a market for today. Thermal electric generators are probably a market for 4 or 5 years out. However, it's a fascinating technology. The idea of recovering heat from the exhaust pipe of a car, using it to enhance the efficiency of the car or for the heating systems at home, or even as a way of bringing electricity into some of the more remote parts of the world where you can take electricity from your cooking pot as you're warming your stews. I think this particular example is from the medical industry, using a thermoelectric generator to power sensors, biomedical sensors. And it's obvious. If you replace things like PET materials in a thermoelectric generator, if you can replace it with a flexible foil with this insulation on, you're going to transfer the heat through more quickly, which means that you're going to get better performance, both in terms of the startup time. So from the point that this patch is applied to the point where it's generating electricity, it's much quicker. And the peak that it's generating is also much, much higher. So you're seeing something like a 36% increase in power, just based on switching over to a different substrate technology. Interestingly enough, it's also cheaper. So that is my wrap-up slide. We're manufacturing this technology in the UK. We're using the technology in markets like the PCB industry, the semiconductor packaging, the thermoelectric generator markets, using it across a wide variety of application areas. In fact, what we're getting out is very significant benefits in terms of the performance that we're delivering and also the cost base. And you can imagine if we're where that slide showed us a moment ago, if that's where we are in costs already, you can see that as we move forwards and start to take some of the costs out of the initial plants when we build additional production lines, that cost model will improve further. It's very much an exciting time for the company on this. Very much in partnership. I mean, this is something that I'm very keen on, is that we're working in a space where there is no point in reinventing the wheel. We are the world leaders in this nano-ceramic technology, but we work with some real experts in individual fields. I could talk about things like the thin film techniques, the sputtering techniques that we're using in the LED packaging industry, where we're working with some real world leaders, or in the metal PCB industry, where we're working very much with Spirit on delivering these boards out to customers. So that takes me to the end, and should I open up to questions?
Yeah, yes.
I think our experience so far has been it can go down standard PCB assembly lines, it can go into the standard ceramic assembly lines also for the packaging industry. The packaging industry, they're not used to something which is ceramic on aluminium. So it's a little bit of a learning experience for them, but in many ways it's an easier option for them than what they're used to. Certainly a lot of the unpleasant processes that they have to go through with conventional ceramics are actually eliminated. And as Steve says, for PCB manufacturing, it falls pretty much straight into a standard PCB manufacturing flow.